Everybody who's here seems ready, but not everybody's here. I'll wait another minute. Okay, welcome back. Today I want to as promised, start talking more about what it means to be robust if you're a system that's subject to some disturbances or uncertainty, modeling errors, the like. We've talked a little bit about that. We talked about it when we did common Lyapunov functions just as an early example, but we haven't really developed the machinery that we want to talk about that well. And I actually think that a lot of people get exposed, especially with the rise of machine learning. Lots of people know Bayes' rule, with state estimation and SLAM, simultaneous localization and mapping, and other kind of disciplines in robotics have brought probability theory into robotics in a nice way. But there are some basic things you just have to think about at least once about what it means to put some probabilities through a dynamical system. And I find actually a lot of people haven't thought those through. I want to make sure I give you I show you a little bit of the beauty that is stochastic dynamics. It's really like, I think pendulums are beautiful, whatever, but this is way better. Okay, so I want to try to give you a little bit of that picture, and then we'll do some of the machinery today and a little bit more on Tuesday about how would you actually write controllers against it, reason about it. Okay, so far in class, we've basically talked about systems of the form like this, where F was potentially complicated, underactuated, and or the discrete time system xn plus 1 is f of x n un. And all I really want to do today is a little bit of a change. You can say it's a big change, but I want to add a new variable in here, which is some sort of random input, okay? We'll actually spend most of our time thinking about it in discrete time because you don't have to think about continuous time noise. And it's just a little easier to get your head around, but this is, I want to think about W, whether it's WT or W of n, right? Are the output of some random process. These are random numbers coming into our dynamics, okay? But otherwise, I'll leave the equations of motion alone, right? So I'm still going to write a determinist, just a function which takes my state and my input and turns it into a derivative or into the next state. It's just that function now has one extra input, which is a random variable, okay? This is a very general form. Wn can be disturbances. It can capture even model uncertainty, if you like. Maybe it changes over time more if it's a disturbance, or less if it's a model uncertainty. But it's a very rich form. You can stick a lot of things in as just something I don't understand coming in as W. What I'm not talking about here, sort of decidedly, is measurement noise, measurement error noise. That is the natural thing. Normally those two come together. I add, a lot of people call this process noise, right? This is also known as process noise. And it's distinct from measurement noise. As soon as you have measurement noise, you have conversations about state estimation and the like. But, and there's actually relatively lots of good coverage of that on campus. I think a lot of people have good courses and the like on that. But I'm going to say, go ahead, even if you can at any time know what x is, you know what your state is perfectly. You don't have to solve the state estimation problem. But you just know that as time evolves, there's going to be randomness pushing on my system. That's like the first cut we can make to really dig into this. And so we'll focus on process noise only, no measurement noise today. Okay? As always, there are special cases that have a lot of structure. We like the control affine thing, that adds a lot of special structure and it captures a lot of our systems. The special structure that often pops up, it's not always, but oftentimes you'll see things that have additive noise. Or some, there could be some BW times, just some matrix times some simple noise, okay? So this is an additive noise. It's a common version of how W enters into the equations, not the only way it can enter. Okay, so what I want to start thinking about is just the basic mechanics of what happens now to my system when I've got some random noise coming in. Okay, and I like to think of it first with, let's just think about a simple graphical analysis, right? So think about a particle in a bowl that's subject to Brownian motion, okay? So I'll have some potential here, I'll call it U of x, and I want to think about this as a physical, like out of marble or something, and it's going to go mostly down, but it's going to be subject to some random noise, okay? Just I don't know, it's a nice, for me it's a physically clean way to think about it. So we'll use this Wx as this is a potential well. And we'd like our dynamics to be the gradient, to go downhill on that potential well. Classically, right, so if you think about the potential well being quadratic, then that gives you a linear dynamical system because the gradients are then linear. So I could have, the first time I talked about linear systems in this, I could have drawn this potential well and said it goes to the bottom. That's a one way to think about linear systems. So let's do that for now, the systems with Brownian noise. So we'll choose just U of x to be 1/2 alpha x squared. And we'll say that I'd like the way you go downhill in discrete time, you'd like the difference to look like the gradient evaluated at xn. That's somehow my gradient dynamics. But I'm going to go ahead and add in my randomness. Okay. So a little algebra. Xn plus 1 is now, if this is just this is just alpha x, right? So I get 1 minus alpha xn plus wn. So let's just make sure we remember what happens when W is 0. The deterministic case, for what parameters of alpha is that stable? I mean, it's certainly got a fixed point at 0. What parameters of alpha is it stable?
Minus 1 and 1.
1 minus alpha needs to be between minus 1 and 1. Right, for discrete time systems, you need to be inside the unit circle, which means alpha has got to be between 0 and 2. Okay, so now let's make W not 0. When W is not 0, the first thing we have to do is W is just Gaussian white noise. IID, independently identically distributed. So I will write that as the expected value of Wn is 0, so it's mean 0 Gaussian white noise. Okay. And the expected value of variance, the covariance of this is just some sigma squared that we're going to pick. I equals j, and 0 otherwise. So at every n, it's a different. It's completely, the expected value across here is 0 if I is not equal to j. So independent times are completely independent, but W is drawn from a distribution with some variance sigma. All right, so now just like we started in class, so if I ask the question, if I give you x0, if it's known, a known initial condition, then what questions can I ask, right? So for linear systems, we've always been able to answer that. But it gets more complicated now, right? Now x of n is a random variable. Even if your initial conditions were completely known, x of n is suddenly a random variable, right? As I move through, I have an entire distribution governing. Okay, so what is x infinity? We at least before talked about the long-term behavior as being an easier thing to analyze. But something's broken here. Even x infinity is a random variable. And that's a simple thing to say. Of course, I've got a random variable coming in, I've got a random variable coming out. But I just want to stop and think for a second. Does this break everything we've said completely in class? Now, everything we've talked about, stability analysis, stability theory, robustness, all these things we're talking about, the ability to talk about convergence to some fixed point, just, this whole notion of stability that we've built tools around. Is this system doesn't have a simple story about stability, right? So we have to throw everything out, or can we salvage something, right? I really want you to think more about, what that is, right? Because xn now is a random variable. And we're gonna write that as a distribution, a probability density function. P of xn is some function, is a probability density function. So it's described by So the fundamental questions we want to ask are no longer about x per se. We don't care about what x does. In fact, what x does on any one execution is potentially very complicated, even for the linear system. What we want to talk about instead is the dynamics of the distribution. This is the thing that's going to be natural, maybe stable, maybe whatever, even though x, the individual traces of x can be very complicated. Okay, and I'm going to try to make that point a few times in pictures and with cool systems. Okay, so how do we go from f, our original dynamical system, to writing the dynamics of the distribution? Well, so I'm going to use my notation, so I can write the probability density of the random variable coming in. I'm leaving off the n because we said it's the same for all time, but I could similarly write like this, okay? This is a Gaussian, so it's given by the density function you probably know and love, or at least know. Okay. Now, by dynamics are given by a conditional distribution, right? The way to think about f in this probabilistic framework is I've now got a conditional distribution which tells me how x plus 1 depends on x of n and wn, and u if I had it, but I'll leave it off because I don't have it right at the moment here, right? So this is some function of 3 variables now. And that's a deterministic function, but I can also say now, taking that into account, what is the probability of just getting the next n plus 1 as a function of n, xn. And this thing is just going to be the density I've put in here pushed through my nonlinear equations. In the simple linear case, it's very simple, but I just get another Gaussian in this case. And in general, I can write this as my conditional distribution. I can look my update equation of how does p of xn plus 1 evolve for some function for value y of this big complicated xn plus 1 xn. It's just the standard rules of probability. This thing is sometimes called the master equation. When it's used to describe stochastic systems. Okay, so my dynamics describe the conditional probability of jumping to the next state given I'm in some state. I have a current distribution over states, and this standard rules of probability tell me how to go to the distribution over the next state. So for the simple case of a linear Gaussian system, the picture you should have in your head, it turns out that if this thing is a Gaussian and this thing is a Gaussian, then this is kind of like a convolution if you think about the convolution, but Gaussians convolved with Gaussians stay Gaussian. So this thing stays Gaussian, and that's one of the classic results that sort of stochastic systems are built on. But it has a very beautiful graphic. I don't want you to think too much about the equations. I want you to think about the implications. So in practice, if I take a known initial condition of this particle in a bowl, okay? Then what is, if I have a known initial condition, I say that x0 equals, what, -3 or something. Then that's equivalent to saying I have an initial distribution over x0 that is a delta function. It's absolutely, all of my probability mass is concentrated at -3. So I'd write that as x plus 3, the delta function. And I would draw it pictorially like a vector here at -3. Yeah, sorry.
Should there be an E, like an exponential on the second degree on top?
Thank you. So if I know my bead starts here, then my initial distribution looks like this. If I take that distribution, drop it in the master equation, in my delta function, and I convolve it, it's not quite a convolution, there's no flip, but, and I push it through a Gaussian to see what my next distribution is going to be, then I'm going to get a Gaussian. A delta function convolved with a Gaussian is a Gaussian. And I'm going to get something here that has the contribution, partly, it is exactly the update here, right? I've got my dynamics are exactly 1 minus alpha xn plus this Gaussian, right? So I'm going to go 1 minus alpha. I'm going to push myself towards the thing the way the deterministic system would have. But then I'm going to spread myself out with a Gaussian. So after one step, I'd expect my distribution of possible states to be a Gaussian centered around 1 minus alpha times -3. Yeah. And then if I do that again, my Gaussian convolved with a Gaussian is going to give me another Gaussian, where every one of these possible states, the way for each one of these, I'm going to take 1 minus alpha times it. I'm going to weight it by that probability. I'm going to convolve that with a Gaussian, and I get another Gaussian that looks like this. Another Gaussian that looks like this as I go. Okay. And what you'll see is that distribution has its own dynamics. Started as a delta function, but then stayed Gaussian. That distribution will converge to a stable distribution. And it'll look like a Gaussian with some width we can compute, centered at the origin. In contrast, the particle on any one, if I were to simulate the particle a bunch of times, in some simulations it might be going like this, all, up here, some down. It might kind of go down there and just wiggle a little bit. It might do a bunch of things. But at no time would I describe the evolution of the particle as reaching a fixed point. It's only the evolution of the distribution that reaches a fixed point. Okay? So now, I really want to transition. I mean, we think about these things flowing through state space and how you want to use control to sort of reshape the vector field to get things to move. Same problem, but just now you've got a whole blob of probability flowing through the vector field. And your job is to yield, you don't get any more actuators, by the way, so it's even more underactuated in a sense, but you have to do more with less, with the same number of actuators. Your goal is to change the vector field so that you can control the way this whole distribution slides through. Okay? Now, if I were to go through and write this for the linear Gaussian case, one of the things you see is that it really does, the master equation really does have a steady state. So if I describe this by its mean and covariance, then there is a steady state distribution. And it has mean 0 and the stationary distribution here, or the looks like sigma squared, the noise I'm adding in, 2 minus alpha, alpha squared. Okay, so this is like the one time we can compute the stationary distribution in closed form. It's another Gaussian, and it has this covariance or variance in the scalar case. As a sanity check, I think you can convince yourself that this thing is well behaved when alpha is between 0 and 2. The denominator stays away from 0. Yeah. Furthermore, if you know Kalman filtering, and you've thought about Kalman filters before, the dynamics of that variance going through here is just the forward propagation step of the Kalman filter. So you can write this in the, for a vector here and a covariance matrix here, and you can write the covariance update and get exactly, it's exactly the result of this equation, and it tells you how that covariance matrix evolves over time. That's just the one half of the Kalman filter, the other half being the process, or the measurement noise. Okay, so the linear Gaussian case is classic, standard, important to understand, but it pales in comparison to the richness of the full nonlinear systems. Okay, so nonlinear systems do cooler, wackier stuff. I mean, you don't actually even have to do that much to start getting really interesting. So, imagine I take that same system and I have my particle going like this, okay, going down a potential field. This, what is that distribution going to look like over time? If I started it like right here, you'd expect this looks a lot like the linear Gaussian, so maybe it starts going down and I get some probability mass here. But the interesting thing is that if you watch any one particle for long enough under Gaussian noise, no matter how small the Gaussian noise is, because Gaussian's got infinite domain, eventually you'll get a very large number out of even a very narrow Gaussian distribution. If you watch any one of these particles, it'll go down here, it'll hang out a little bit, but then it starts making something that people call escape attempts. I love that. Right? So eventually you'll see particles kind of go up and then come back down, come up and go back down. And with some probability, they start leaping over here and they kind of spend some time over here. Okay, so your initial probability mass starts like this, goes down, but as time evolves, you'll start getting some probability mass over here. Okay? And maybe you won't be too surprised to see that the relative sort of size of this, you can get the stationary distribution of this is going to have a smaller bump here than over here. You'll have more probability of being in this larger potential well than you'll have in the smaller potential well. Okay, but like I said, every individual trace has particles that are trying to jump across. Right? This has implications for control and for stability. Oftentimes, this notion of having like a region of attraction, for instance, let's say I have some guarantees that I can control a system under some conditions or from some states, which is, this has got a region of attraction like this for the deterministic system. But now I'm applying some Gaussian noise, okay, there's a finite probability of it leaving my region of attraction at all times. And so things get interesting. Right? Even if I'm at quadrotor, I've got a guarantee that my quadrotor, no matter if it's in these sort of configurations, I know it's going to be stable. But now the wind starts blowing, it's going to be knocking me around. If I wait long enough, there might be some amount of wind that'll take me out of my region of attraction. Okay, so you have to be very careful about thinking about the implications of these. I like thinking about, I like visualizing how these things go, right? So here's basically that particle evolution. This is just the cubic the cubic polynomial that has the two fixed points, one here and one here, and that's the histogram of possible particles as it moves along. So I'm using the words particles because a way to represent numerically these distributions when you don't have a closed form solution is you just do a lot of random samples and think of them as particles that are all running at the same time, and then just count the particles and plot the histogram as our sort of numerical approximation of this object. Okay, so that does sort of what you'd expect. Yeah.
For the transition distribution, should it be 1 or y minus alpha times x? Like on the second line.
This line here?
Yeah, is it y minus 1 minus alpha times x?
Yeah, I did that. I left out the 1 minus alpha. That sounds right. It should have the dynamics here. So it is 1 minus alpha times x. Like this. That looks better, right? Thanks. Okay, so the stochastic thinking is just starting to flow. I think this maybe makes sense. So here's a thought exercise to see if you're following along. Let's say I take the van der Pol oscillator. Okay, and I'm going to start it. Remember, the van der Pol oscillator has a deterministic limit cycle that looks like this, right? And let me say I'm going to start it here, known initial condition, but I'm going to add Gaussian noise on every time step. I'll do the discrete time approximation so you don't have to think about continuous noise, but what is going to happen to the distribution over time of the van der Pol oscillator with Gaussian noise?
It should start moving around the circle and then it'll like sort of spread out, just like become a thing that is centered at the circle. Well, not circle.
I think that's exactly right, but do you have a version of it?
Will there be some stuff that ends up at 0 as well?
So because it's Gaussians, it will have some mass at 0, but I think the bulk of it, so I think, well, let me just show you. Here it goes, a lump of probability that starts going around. That's kind of what you'd expect, right? But if I speed it up a little bit, the system is stable to the limit cycle, but it's not stable along the limit cycle, right? So any noise that pulls it apart along the orbit will never be pushed back. So you'd expect that eventually it'll stretch out and have a distribution that if I stop at 1,000 or something, but it'll have a distribution that is roughly a tube around the limit cycle. But not exactly. It's going to have a little bit more mass even at the steady state in some clumps where things kind of, a little bit of congestion, a little bit of, right? It's pretty beautiful. Beautiful stuff. Okay, so probability is awesome. Pushing it through dynamical systems is, you get all kinds of rich behavior for nonlinear systems. The question is, how does it work for control, right? How does this screw everything up? I guess one more example is it actually works well even for, it's perfectly well defined, but it's even richer again if you talk about hybrid systems. So now let's say I have a walking robot that is making and breaking contact with the world. I'll stop this so that, actually I can't, I'm not sure I can stop it. Is that going to stop? Actually, I can't cover it up. That's the one thing, somehow the matplotlib draw says, I'm going to consume your screen. Okay, let's think about my favorite example of a hybrid system, of like a walking robot, walking on, let's say, rough terrain. That's a nice way to think about randomness coming in. So we've got, we've talked about flat terrain or even down ramps, but what's sort of a simple example of a system with noise that matters in walking is it's rough terrain, okay? So imagine, actually the simplest example is the rimless wheel again, which we know the dynamics is governed by some alpha. And if I think about now suddenly the rimless wheel's on some rough terrain like this, it's actually clean and good because you might ask, how do I parameterize a domain, rough terrain that looks like this? It could take arbitrary shapes. Maybe I need to get rocks. Maybe whatever. But because the dynamics of this thing only matter when the foot hits the ground, and the foot hits the ground in these intervals here, actually the only thing that matters is the height here, the height here, the height here, the height here, assuming I don't clip my foot on the way down. It doesn't have any spikes or something that intersect somewhere else. Okay, so all that matters is the sort of finite values that this random terrain takes at the footstep intervals. So the model I like is actually alpha n. Each one of those, by the way, we could just be thinking of as a slightly different ramp angle that happens for one time step. Okay? So we can think about our equations of motion by just saying, I've got my rimless wheel equations, but my dynamics are governed by alpha n is now a Gaussian random variable, let's say. If I assume the rimless wheel is never going to go back uphill, then it's fair to just say that it's always independently drawn random variables. Okay. We know everything about the deterministic fixed points. There's a rolling fixed point and a standing fixed point. It's basins of attraction. We did that through the Poincare analysis. What can we say now about the rimless wheel rolling down rough terrain? Okay, so it turns out the first time I drew the rimless wheel's return map, we did it collision to collision. But since that's changing all the time, let me do the apex to apex map instead this time. It's still a passive system, so I've got no control to worry about. It's one-dimensional map. Okay, this is the line of slope 1. And what I'm going to talk about is the theta dot at the nth apex, which is theta dot at the n plus 1th apex. And if we're always rolling forward here, the apex to apex map looks something like this with a single fixed point. Here, that's the deterministic apex to apex map of the rimless wheel. That's just same plot I already made, but just in a different coordinate because I'm plotting it at the apex. Okay, so now my ramp angle is a Gaussian. I guess I called it that was my gamma. Alpha was my inner leg angle. Sorry about that. But now this is a random variable. So basically, the way to think of it is that my function here, which described my return map, is now, I have a random variable here too, right? So if I'm at this place at one time step, then there's a whole distribution of possible outcomes that I could get. So I'm at the limits of my artistic skills here, but see if you can work with me. So let's say I'm right here. Where am I going to be on the next time step? There's actually, there's slightly different curves depending on what gamma is. Okay, and each of those gammas comes in with a different probability. So the picture I like here is that I've got like a distribution over possible outcomes. It's not quite a Gaussian, it's pushed through the nonlinear dynamics, but something that's like, given I'm at theta dot n at this apex, there's some range of solutions I could be at the next apex. Yeah? And that's true along all of these, you know. Is that good? Yeah. And then there's something else that can happen is I can fall off the end where I didn't make it over the apex and the robot stops and stands still. Okay, so there's some tails here that maybe correspond to I didn't make it over the top. So it's suddenly very interesting to think about this. This is really a discrete time system because we're looking at apex to apex map. How does it evolve as a probability distribution evolving over time on this iterated map? Okay. What can you say about the long-term behavior of the system? I don't know if it's easier to think about the pictures or easier to think about the experiment. Both are fun. If I come back to your experiment, you know, a million years later, what's the rimless wheel doing?
Stopping still.
Good, right? It's exactly like this picture, except for this one's an absorbing state suddenly, right? So the rimless wheel is going to go along. It's going to bounce a little faster, a little slower, but it'll slowly make escape attempts. It'll get, you know, there'll be a sequence of solutions that make me slow down enough that eventually I'll hit something that stops me and I'll stand still. And since that is called an absorbing state of my dynamics, which once I'm there I won't ever transition again, that means as time goes to infinity, the probability of being in that absorbing state, standing still, goes to 1. All right, so the stationary distribution the only sort of long-term solution is standing still. Okay, now if you're a walking robot person and you work really hard at making your robot not fall down, this is sort of a grim statement. If you know, okay, as soon as I put probability into play, basically at some point it says my robot's going to, this one can only stand still, but the equivalent is my robot's going to eventually fall down. Right, so people really don't like when I say this, like people who work really hard on their walking robots. But if you have any sort of stochastic dynamics involved, sorry, you know, eventually, certainly anything with tails like a Gaussian, you know, at some point something bad's going to happen and your robot's going to fall down. I don't know if it's like a gust of wind coming off the Charles or like a semi coming down Mass Ave or something, but that robot's going down eventually, given the model you've told me, right? So, you know, maybe that doesn't change the way you build your robot, but it does have to change the way you do your analysis if you're going to do the stochastic version, right? So what I said here was we need to change our thinking to shape the stationary distribution. That's good for this problem. For linear Gaussian systems, my goal should be to shape the stationary distribution. But I'm saying no matter what you do with your design or your control or whatever, your walking robot's going down. That's the only stationary distribution. So are we done? Right? Somehow there's got to be a little bit of a different story. And the different story is that there's a really interesting long period of time before you fall down, so where your distribution is still meaningful and should be controlled. Okay, so there's this concept of a metastable distribution. These are long-living transients for our case, P of xn. So if I have a system that goes and hangs out with some distribution for a really, really long time, and eventually that probability mass disappears, it can still be meaningful to devote control effort to trying to make my long-living transients perform as well as I can. Okay, I've got cool pictures for this. First of all, this is that's just the particles over time. I forgot to show that, but okay. Here's my rimless wheel. Ready? Rimless wheel on rough terrain. Here's the distribution. You see what I'm going to plot it as this function here. That's the return map is the blue line, okay? And the red is the histogram of particles, which I can plot along either axis, but I'm going to plot it along this bottom axis here. Okay, we're going to watch how that evolves over time. Okay, so there is an initial transition where that thing goes to something kind of like this, right? And it's centered around the fixed point, the way we want, the rolling fixed point. And that thing hangs around for a while, but it's not actually a stationary distribution of the dynamics, because that thing, it's like, it's got some probability mass there. It's meaningful. We should control it. We should shape it. But you also have to accept that it's slowly going. And as time goes to infinity, that's going to have no mass, and there's going to be all the mass at the standing fixed point. Okay? So again, we have to sort of think about what we're asking for. Controlling the fixed points doesn't always work in this case, right? This is now controlling the transitions, but it's just as meaningful. And there's good mathematics to sort of pull out those transitions out. So sort of in a philosophical discussion about these kind of ideas in the walking community, we were trying to advocate for, stability is kind of the wrong, if you believe the world has got any disturbances thrown at you, maybe stability is the wrong question for walking. What you really should think about is mean time to failure, which is in this picture is the mean first passage time. You can talk about the first what's the probability if you start here, at some time I'm going to make a first passage over to this side. So there's an idea called a mean first passage time. And what I care about, since especially for the rimless wheel or for any robot that can fall down that has an absorbing state, what I care about is the mean first passage time to this other part of state space, my falling down state space. Okay, and there are tools and stochastic processes to try to estimate the mean first passage time, and that maybe that's the metric we should be thinking about. Okay, and it's good. So it's equivalent if it's a robot that's going to fail when it falls down. That'd be like saying we should be trying to think about the mean time to failure as our metric instead of absolute stability, because that's too rosy of a picture. There's one more animation here that I think is cool. So this is showing the return map in the original coordinates. Now it's on stochastic terrain, and you could think about this as a stochastic return map. Here we go, boom, boom, boom. So that's what the return map looks like over time. That's what the distribution looks like over time. And eventually you have the statistics of your long-living metastable distribution. All right, so we've talked a lot in this class, and we've gotten, I've shown real robots working without talking about any of this stuff. So I think it's important to maybe take a quick step and say, when do you need all this? I don't want to just say that everything we've done is wrong, because clearly it wasn't. So when do you have to start going to this kind of modeling? And I think it's actually fairly clear. So in the walking case, there's maybe two types of situations, right? So the situation, I'm sorry, I forgot to reorganize the videos there, but the situation on the left, I would call that hilarious but a rare disturbance, right? So you can spend your time writing controllers. You could write down, what is the probability of being kicked at time t, right? And do your controllers about that. But probably you don't have to. If you have stability of your dynamics and you have a big basin of attraction, then that captures this idea that if, so ideally the basin of attraction, I'm going to just evolve according to my dynamics. But if someone were to kick me, this impulsive rare disturbance, then that's like someone picking my state up and moving me to a different part of state space. And if I have state stability via Lyapunov function's region of attraction, then I'm covered by my original analysis. This, on the right, I think is a pretty different situation. The nominal model is just not correct, right? Every footstep is changing my dynamics. So if I put the blinders on and say I'm going to only analyze the nominal model, then it's not true that the convergence of my model is governed by the original differential equation. Because I'm getting bounced around constantly. So the stochasticity, so in the first case, because it's a rare event, it's meaningful to follow the evolution of the time dynamics of my system under the unperturbed dynamics, because I'm going to have long stretches where my dynamic model is fairly reasonable. In the second one, where the noise is affecting me on every time step, it's more important, I think, to switch to the stochastic analysis. Right? And of course there's a whole spectrum there. But as the contribution of the noise increases compared to the contribution from your original deterministic dynamics, and you should think about this as a pushing and a pulling, right? So there's two forces at work here. There's the stability that comes from my deterministic dynamics. That's making my distribution smaller. As I make the system, as I make that bowl steeper and steeper, my linear system stabler, more and more stable, then that's going to force these distributions to be tighter and tighter. As I add more noise, that's going to push it out. So stability is trying to pull my distributions in, and uncertainty is trying to push my distributions out. The more my uncertainty affects, as my uncertainty's effect grows relative to my stability, you got to start worrying about it. Right? If you've got massive powered actuators and big feedback and whatever, you can probably just ignore it. Right? Even if someone's pushing a lot, if it has no effect compared to my actuator power, it's all good. Let me just take a breath there. And so, do people feel like that sort of resonates, or how does that work in terms of like what you're thinking? Yeah. Questions?
How should we control differently given stochastic environment?
That's what we're doing. That's what we're talking about next. Okay, let's do that. So there's a handful of different ways that people will change the control, and you have to think. I wanted to do this first because some of these you just really have to think about what you're asking for. If you're asking for absolute stability, of course that'll fail. If you're asking about long-term stability or probability 1 guarantees, depending on your uncertainty, that may or may not fail. I used Gaussians as an example, but you could imagine if my uncertainty was always between -1 and 1, then I'd get a different picture going down here. And it might be that I actually have I could have, let's say, after this, I'd have a box. Let me draw it right below. Let's say W was always drawn with a uniform distribution of some small amount, okay? Then maybe my time evolution would look like this. I'd have after this I'd have one function, after this I'd have another function, after here, and maybe my stationary distribution looks like a box there. This system, this one has probability mass everywhere. So if I say with probability 1 I want to be near the origin, I can't do that with a linear Gaussian system. But there are other distributions where I could do like a worst case analysis and say I want to make absolutely sure that as time goes to infinity I have all of my probability masses in some finite region. And those are fundamentally different ways to approach the control problem. So I would distinguish between worst case control design and analysis, where it typically only makes sense if you have a bounded uncertainty model, right? Right, so P of W has a finite domain. And we've actually already done some examples of that. One example, even just for analyzing that, was with a common Lyapunov function. Do you remember the example where I said we have x dot equals a of x, but a is an uncertain parameter? It was the sum of some affine combination of the I, bi. And then we found a Lyapunov function that worked for all a's. And so showed that was like one of our first examples of semi-definite programming. That's an example. I could write that as in this form. That's an example of a bounded uncertainty. The worst thing that I can do from x is limited. I've got some bounded uncertainty. I know that a is inside of some convex hull of these. So the difference between my nominal is going to be bounded, and I could find a Lyapunov function and say, as long as for all of the possible values of w, right, v dot is going less downhill, then I can do a lot of my standard control design like that. Okay, and robust control has lots of tools for that. Most for linear systems, but there's some for nonlinear systems. Okay, but it's often it's often criticized as being too conservative. That proving something for all w means that your controller has to be fighting the worst case all the time and tends to lead to conservative control. I'd say the second approach is to do stochastic control, where your objective for control is instead to put some measure on the probability distribution and try to control that. Right? And it gets harder, but there's a few special cases that are good. I would describe the field of robust control as actually covering both of those. There's good tools for worst case analysis, but also for stochastic analysis. And I'll get through a few of them, but unfortunately there's a whole class to take on that. I'm not sure if we actually have a class. There's, if you can get the right person teaching, for instance, 6.241, you'll get a lot of robust control in it. There are some robust optimization classes in in operations research, but they're not quite robust control. So, okay, the annoying thing about robust control, and I'm sorry, I'm on the record here, right? But, so the robust control community is so smart that they write papers that nobody can read. I think they've done a disservice to themselves in the sense that there are beautiful theorems in Hardy spaces and Banach spaces and the like, and you actually don't need any of that to understand the concepts, but unfortunately, you do need that to read the papers, like to even read the abstracts of the papers in many cases. So it's a little bit of a hard field to penetrate, and it shouldn't be, but sorry. Okay, so in the stochastic control, you'd say, like, I'm going to write my objective directly on controlling my probability distribution of x over time. Okay, and the most common by far is to try to optimize some expected value. So if I have some cost function, my cost function becomes a random variable, and I'd like to say on average it performs well. That's, you'll see in a second why that's a natural and easy thing to write down, and people gravitate towards it. But before we write down the equations, which I think are compelling because of their simplicity, but you should stop and think, is expected value what I really care about? There are a lot of times people, I think, use expected value without maybe thinking about the consequences. If I have an autonomous car, right, and it performs really well on average, every once in a while it drives off the road. That's probably not a good objective, right? Maybe, but also, worst case analysis is actually not good enough, because if I write the rules of the road and the laws of driving in Massachusetts, and I say drive down Massachusetts Avenue and give me a proof that it's always valid, my proof machinery is going to say, sorry, impossible. And it'll just stay in the garage or something like that. Or we don't have garages; it would stay at the parking meter. Right. So there's something that's not quite compelling about either extreme of doing the average case performance or the worst case performance in a lot of real world settings, I think. So there are richer languages here for somehow, like there's risk-aware control, which I won't cover, but it's worth reading if you like this kind of thing. Where, for instance, you might say, I'd like to put a bound on the mass, the probability mass in the tails of my distribution. Right? So I've got. I could say that my distribution never crosses, like this. Let's say this is my bad area, and this is my probability of x. Right? I need to stay in here to succeed, right? I say worst case analysis says my distribution has to be inside here always, and that's good for some problems, and if you can get it, more power to you, but it might mean you're too conservative, right? Expected value says I just want to make sure that on average I stay inside there, and that's a reasonable thing to ask, but maybe not good for an autonomous car or an airplane or whatever. But there are other statistics that you can imagine. What if you said, like, I'm going to try to estimate the total probability of my system as it runs, and I'd like the mass of this, the probability mass under the tails of the distribution in the failure region to be small, right? And that gives you into this sort of risk-sensitive, risk-aware control. Another name for this is chance constraints. And it's good stuff, and there's it's an active area of research, and there's good work to be done there. Times you can use convex optimization for it and the like. Of course, there's times where it gets pretty hard pretty fast. Okay? Let's see why expected value is such a good case. The expected value, by the way, is what pretty much everybody in reinforcement learning uses, right? And it comes down because reinforcement learning, the roots of which we'll cover soon, it's all in dynamic programming. So originally in dynamic programming, we talked about having additive cost functions like this. But now, if x has become a random variable, suddenly that means j is now a random variable. So a natural thing would be to say, I'm going to minimize over u the expected value of j. And the expected value, is a linear operator. It comes inside the summation, and that's what really is this huge, big simplification. So this thing is equivalent to minimizing the expected value of g of xu like this. And therefore, you can do value iteration and other operations on it with very little added complexity over what we did before. But just because of this, this simplification is good. I can take my expected value inside that sum. But remember that the expected value here is still a rich thing. This thing on the inside still has all of that in it, right? Like all of this stuff I talked about with distributions being complicated and everything, right? This thing is still on the inside is the integral over x g of xu, let's say, times whatever my p of x distribution, right? So the estimating the expected value of g at some time step n means bringing in the entire dynamics of the distribution of state over time in order to evaluate that expected value, right? So this is one good simplifying step, but it's still got all the richness of nonlinear dynamics and stochastic dynamics inside it. But interestingly, taking that and using it as an objective for control can really make a big difference in the way that your control design comes out. So if you were to use this in a dynamic programming recursion, it's again limited in state space, but here's an example of doing it for the compass gate on rough terrain. Now it's on flat because it's got an actuator at the hip, right? And it's very interesting. It's very interesting that if you just optimize take the original deterministic problem and do value iteration to try to come up with a policy for the hip, then the robot takes like one step and falls down. It falls down very, very quickly with very low changes in terrain. If you instead optimize this objective, where the goal is just to not fall down, then the controller that comes out is fundamentally different. It becomes a more conservative. It has no information about the terrain. It's like walking blind. So what it ends up doing is it takes a more conservative, instead of just sort of scuffing its foot and going like this and risking collision and failure. Sorry, wait. It takes a more conservative, like lean forward and come back like this, and that makes a marked difference on how well it works on rough terrain. It'd be better still if you used a sensor and looked at the terrain, of course. Okay, but if you have this model where I don't know what's going to happen to me and how do I be robust, then it evokes a control design which gives you a more conservative strategy. And that's a good thing. Okay, but there are some subtleties in that. Again, thinking about what exactly do you ask of your system given this. you remember that if I take, for instance, even the quadratic regulator cost to stabilize my pendulum, and I write it in this form, and now there's some noise, and I'd like to do value iteration, or I'd like to do an LQR derivation on it. There's a couple things that should give you pause here, right? One of the reasons that our original cost function for LQR was a good cost function that worked as time goes to infinity is because I knew that the cost was eventually, if it was a stabilizable system, that the cost would eventually go to 0. So this integral over an infinite time was still going to give me a bounded response. Okay? And something breaks here now. If I say, even as the pendulum goes to the top, it's going to be bouncing around forever, then my cost function is actually not going to go to 0 over time. And I have to, is this a meaningful quantity, or does it just blow up to infinity, and therefore I don't get a meaningful control out of it? Right? So there is the stochastic version of LQR. The way we write it is like this. This is Gaussian IID. Mean 0. So what do you think will happen? If I have my original objective function, but now it's the expected value of the sum as n goes to infinity, x transpose qx plus u transpose ru. What do you think is going to happen?
If it's not in 0, where do you put the outset?
That's actually, so I could add a plus c here and have an affine system. I could, in many of my derivations, it's okay to have w be a more complicated function. In the particular Riccati equation, I'm going to assume it's mean 0 in order for the math to go through. But in general, the modeling framework says you can give me any distribution for w coming in, and I'll push it to a deterministic function. In practice, so for instance, like architecting the way you write systems in Drake, I made a specific decision to say that w coming in is always of a simple function. It's either a univariate Gaussian, a univariate, uniform distribution between 0 and 1, or one of only a simple functions, and then you could multiply it by any complicated function as soon as it goes in to describe arbitrarily rich systems. And that just makes the analysis better, because I can write more algorithms saying that the input here is a Gaussian or whatever. So that's a standard form, but not a required form. Okay, so what do you think that happens here? Ideally, you come out with a solution that says u equals negative kx, and you do. And it's, one of the best and worst things that happen in control theory is the fact that it doesn't change your solution in the linear Gaussian case. The reason it's the worst thing is because people then go on and assume that you can just do state estimation and then take the mean of the state estimator and use it in your control, even when you have a nonlinear system, and it's not true in general. This is sort of one piece of the separation principle. True for linear Gaussian systems, not true in general, but it's so attractive that everybody does it. Okay? It turns out your control design doesn't change at all. But your cost to go function actually goes to infinity. J of x equals infinity, always. But it happens to equal infinity in a particular way where it's x transpose Sx, where this was the original S, plus some constant that grows to infinity, which looks like the sum as n goes to infinity of the expected value of Wn. So it's a bit like the metastability thing where there's some component of the cost which has this meaningful structure that we already knew about, but actually that nice quadratic Lyapunov function that we have, the cost to go function we have is like this, but it's just going up and up and up and up and up the longer you roll out your value duration solution. So you have to remove the constant term. The same thing's true of the compass gate walking on rough terrain. The probability of failure goes up and up and up and up, but the controller that comes out is still meaningful. Okay, so today's all about just getting you thinking about these things. So one other cool example, which is how do you take an airplane or a quadrotor or something and make it work in the wind? Okay, so here's an example of Joe, who did the video I showed last time with the perching Lqr trees. He actually made a power line with a big fake power line, and he put a magnetometer on the plane so he could localize it during the flight, during the perching, and he was landing on power lines. And then he took it outside, and the wind started blowing, and little foam plane, one actuator, barely in control, big gust of wind, can sort of totally hose you. Woohoo! The status center is like an adversarial aerodynamic environment, I think, but still. Or maybe all of Cambridge's. There's one more funny one. Yeah, like every one of those, the pause is not just like him setting it up, it's like him rebuilding the plane, right? Okay, so it turns out that you can build a better controller that stabilizes against it, and he did in the perching example too, but the toy problem is a quadrotor or his was an aircraft blowing in the wind, and it turns out you can regulate very, very nicely if you're willing to do the stochastic design, and there's a simple trick that's so good for systems like this, okay? And it's an important idea. So if I think about my UAV as having some state dynamics, x of n, to loop around to some controller, right? Gives me a u, and I've got some exogenous input like this. Then I could just do stochastic Lqr and run it. Okay, but that actually doesn't work very well because wind is not Gaussian IID, right? Why do I say that? So, I mean, if it's blowing 3 meters per second at one instant, then on the very next time sample, it's probably going to be blowing something like 3 meters per second again. It's probably not going to be going completely in the opposite direction. There are correlations over time in the actual wind. Less so in the on the status center than in normal places, but still, there's temporal correlations. So the way people often model that actually is with a filter here. So this is a coloring filter where you say that the wind model is Gaussian put through some low-pass filter, let's say. And this gives me my actual wind over time. That's a reasonable way to model wind. There's a couple famous models. There's the Dryden model. There's the whatever models, the von Karman model for wind, and there are different sort of choices of how you generate these kind of functions. Random variable in from a Gaussian IID, put through a low-pass filter, comes out. Okay, so what does this mean for my control design? If I take this now and put my low-pass filter here, and put W in here, then I actually do have a system, this system, which has a Gaussian IID input. Right? I can do LQR on this system. Even though it's still just a low-pass filter, some people think of this as the whitening filter idea, that you take this in order to whiten the input to it. It's called a whitening filter. It makes your colored noise look like white noise. Okay? And then you can run LQR on that system and get good results like this. But what's the trick? So I get the output is U equals negative kx, right? What's x in the controller that I now have to run on my whitening filter system? It's the state of the UAV, of course, yeah?
The current wind loss difference.
Exactly, it's got this low-pass filter has some state dynamics too. So the recipe that this gives you is you have to run an estimator on the wind as well as on your UAV. You're doing a current estimate of the wind state, which is described by the state space model of your low-pass filter. And then you combine both of those into a controller that takes into account the wind state and the quadrotor state to make a control decision. And LQR tells you the linear control will work well in some approximation. And that gives you surprising robustness. And Joe continued to do that in the time varying case and the like. And we have this anemometer that looks like it came from Honey, I Shrunk the Kids. This Doppler anemometer. It's like it's a pretty cool looking device to measure the wind outside and do its thing. So that's pretty good. Okay, so the last slide here is funny. LQR doesn't solve everything, and actually the limitations of LQR were maybe part of the discussion that started the field of robust control. And there was a paper that is pretty famous here. John Doyle wrote a paper in Transactions of Automatic Control in '78. Guaranteed margins for LQG regulators, linear quadratic Gaussians. You guys know this paper? Anybody? Abstract. There are none. Classic, right? So if you actually care about guaranteed performance, LQR gives you nothing, right? So there's more. So on Tuesday we'll talk about the worst case analysis picture of this more. Okay.